Good morning all. Today I'm going to take a look at this all-white monolithic plastic box. Yes, it's a bit too big to fit on my desk, so instead I'll show you this. It's a Silent Night Thermoelectric Dehumidifier, which I saw in Lidl. It was £44. I couldn't resist. It was a bit of an impulse purchase. So today let's have a look at it and see how it works. So first let's take some screws out. And that way I can get the, I think it's the front cover off, and then we can have a look at the gubbins inside. There are 6 screws, 3 down each side. Strange position for the AC inlet. It's mounted there on that very thin edge. Okay, there are also 3 little countersunk screws along the bottom here, which I've removed. And now it's open, but there's a wire running up to the on-off switch, which you can see there. So fortunately it's on little spade receptacles, so they will pull off. That means I can get rid of that bit. No, it's the back that comes off, because this piece is the front. Right, let's take a look at what's inside. Right, let's turn it this way around, so the top is at the top there. There are 2 heat sinks here, and you may be able to see that they've got water on them. Now this hasn't been switched on since yesterday, so that water's just sat there. And of course these normally sit vertically with this at the top, this at the bottom. So these heat sinks are sitting on top of thermoelectric coolers or Peltier elements. I have one here. This is actually much bigger than the elements under here. These are quite small. I'll try and show that in a moment, but that is a thermoelectric cooler, a TEC, under these 2 heat sinks. Now these heat sinks are an interesting shape. They've been cut at an angle and an angle again at the top, and that's so that they can keep cutting multiple extrusions. The angle at the top is not really necessary, but the angle at the bottom is very important, and that's so that the water that collects on these cool surfaces, because these are the cold surfaces, runs downwards onto the tips of these points and then drips into the collection bucket, which sits below these coolers. Here's the collection bucket, which slides into the front of the unit. There's a little ramp there to push a micro switch, which says that the collecting bucket is in place. A second micro switch sits on top of this plastic thing, which if I put a screw into, I can lift it, so you can see that raises and lowers, and that's simply a float. If we can have a look inside without me tipping the water out, yeah, that float lifts up when the water level gets to a certain point, pushes this nozzle up and presses the second micro switch. This is an emptying hole, so you can empty the water out of it, and this is the entry hole with a sort of oval shaped collecting area. So the 2 heat sinks sit some distance above here, drip down into this tray, and then eventually that runs down into the collecting bucket and water collects in there. So how does a dehumidifier work? Well, essentially all you have to do is create a cold surface and waft a bit of air across it, and then the moisture in the air will condense on that cold surface, and the water will collect on there until there's so much of it that it's too heavy to sit on this, which would be vertical, and drips down off these points into the collecting bucket. Now the difficulty is, if you create a cold surface, you inevitably create a hot surface, and on this machine you can see that the hot surface is on the other side of the Peltier elements. Can we see those Peltier elements in there? Possibly not quite. I'll try and get a better shot of that. So these are the thermoelectric coolers or Peltier elements. There's one there, the white block between the 2 heat sinks, and there's another there, the other white block. And you can see where the wires come in, the red and black wires going into those Peltier elements, sitting essentially between 2 sets of heat sinks. The cold heat sinks here and the hot heat sink, which is this one here. So these thermoelectric coolers, these Peltier elements, suck heat out of the cold heat sinks and move it only a couple of millimeters, because these things are not very thick. That's how thick they are. So they move that heat a couple of millimeters onto the other heat sink where the heat builds up. Now, of course, that heat needs to be removed, because if you let it build up indefinitely, this side just gets very hot. And actually, the heat will track back through the semiconductor junctions of the thermoelectric cooler and start to put heat back into the cold side. And you don't want that. So you want to get rid of the heat that's building up on the hot side. And for that, there is a fan. You can just about see the outline of probably a standard 12 volt computer fan. And I know it's 12 volt because up here there is a power supply which has mains in, has all the usual mains side components and low voltage side components. And there are some markings down on this corner of the board. I'll try and get in on them. Well, it's a little tricky to get to, but you can just about see there it says plus 12 volts. Was there a plus? No, just 12 volts. And then here out 5A. So I'm guessing it's a 5 amp 12 volt power supply. Now, to make this work officially, you need to blow air over the hot heatsink, which this fan does, blows over here, and the air is expelled out of this side and out of this side. And when it's running, you can feel warm air coming out of these two sides. But you also need to blow air over the cold heat sinks, because if you don't refresh the air that's here, then it'll be dry air, and you want to keep bringing in new air to suck out more and more moisture. Now that's affected by air is blown out of these two vents, and they come straight out of vents on the side of the entire enclosure. The fan is blowing air from just this empty void inside the case out of these outlet ports, and thus it creates a partial vacuum in the box. And then the only other vents are these, and they sit over these cold heat sinks. So due to the partial vacuum inside the box, it sucks air in through these vents, and that means you're getting a constant refreshing of moist air over these cold surfaces, and so that the moisture can condense out of that air and form water on these heat sinks. So although the fan is positioned to blow air across the hot heatsink and thus remove the heat and blow it out into the room, the secondary effect is that air is sucked in through these vents and therefore wafts over these cold side heat sinks, and that enables the condensation to take place and therefore water to be removed from the air. Now, as well as the power supply here, 12 volts 5 amps, and the computer fan in there, there's a board at the top here, and into it plug the two thermoelectric coolers. They go in on these Molex connectors at the top. There's a connector going in, supplying 12 volts to this board. The fan is this little connector on the side here. It looks like they've put a second fan port there just in case they wanted to use two fans. And then also on this board are a couple of lights, one green light to say it's on, and another light to indicate when the water tank is full. I think that's probably a red light, although I've not seen it yet. The float to indicate that the water tank is full will be one of these switches, and the other one simply detects the presence of the water tank, which sits in this area here. The mains inlet is down here. It's a figure of 8, and that's actually it. That's all that's in this unit. So it's very simple, and it works in really the same way that a refrigerant based dehumidifier works. It just creates a cold surface, wafts air across it in order to collect the water, and then it just drips off. But the heat pump in a refrigerant based unit with a compressor and pipes and all that stuff, the heat is actually moved fairly large distances because there is a medium through which the heat can pass, which is the refrigerant. It can move a significant distance. The real difference here with thermoelectric coolers is that the heat is only moved a couple of millimeters. It's a tiny distance for the heat to be moved. So you have to have the cold side heat sinks very closely spaced to the hot heat sink. You've got to keep the hot heat sink cool, which is why the main effort of the fan is directly to cool the hot heat sink, and then there's a secondary effect where it sucks air into the box and therefore wafts new air over the cold side heat sinks. But yeah, the mechanical layout of a thermoelectric dehumidifier has to cater for the fact that the heat pumps have this very tiny distance over which they operate. Now, if you have one of these thermoelectric coolers, and you can get them on eBay or AliExpress, then you can experiment with heat pumps just by connecting it to a 1.5 or 1.2 volt cell and feeling the effect of the heating and cooling. Okay, that battery was flat, so I've got another one here. So if I connect that up, then yes, I can feel that that is the warm side on the back there, and the front where the lettering is the cold side. Now I'm just charging up my thermal camera because it does have a tendency to flatten its own battery, and then hopefully we can see the effect of the heat pump moving heat from the cold side. No, this is the cold side, from the cold side across to the hot side, and therefore you'll get a temperature differential between the two sides. So when that's charged up, I'll try and get a shot of it. Now I was just wondering if I can show this working. So I've connected the switch contacts together. I'll put some mains in here, and we'll just see if water visibly appears to collect on the cold side. Right, switch on the mains. It hasn't come on, that's because I need to press that micro switch. Okay, I'll find something to hold that in. Right, I found a screwdriver that just sits in there holding that switch in. Now I can feel air blowing out of the two sides of the hot side chamber here. So that should be warming up, and this cold side should be cooling down. Yeah, that feels pretty cool. The question is, will we see moisture forming on these heat sinks? Let's get in a little bit closer. And yes, the place I can see it forming best is this lower edge. And of course that's nearest to the thermoelectric coolers, so that's going to be the coldest point on this heatsink. And in fact you can see the water there forming, and the little bubbles of water, the little droplets of water coalescing and forming bigger droplets of water, and eventually those droplets will become so large and so heavy that they'll fall off the heatsink down on actually to the hot plate, the hot heatsink. Because this thing's lying down, it would normally be standing up, and the water would run to the edge of these tips and then drop off into the water collecting bucket. But I think you can see there, I was just blowing on the heatsink, the moisture forming and the droplets coalescing into larger droplets. Yes, I think that shows it well enough. Now the manual says that the unit is rated at 70 watts, and indeed I've put a power monitor on this thing, and it does appear to draw 70 watts, even though the power supply we saw inside is rated 12 volts 5 amps. Well, that's 60 watts, so it looks like they're overdriving that power supply a little bit. Now the 12 volts goes to the thermoelectric coolers and the fans. It's all drawing from that power supply. Elsewhere in here we have some numbers here. It will pull in 600 milliliters, so that's 2 Coke cans per day. Now by day they mean a full 24-hour period. You really do need to leave this thing switched on for very long periods of time. At 30 degrees, so the air temperature has to be 30 degrees, because the colder the air running into this unit, then the relative temperature between the cold heat sinks and that air means that the unit is less effective. Now I don't know many houses that have their temperature set at 30 degrees, So you won't get 600 millilitres per day because your house is likely to be colder than 30 degrees. It also requires that you have 80% relative humidity of that air. Well, at the moment it's raining outside, so we probably do have that. Yes, it is a bit of a downside of this HTA1 that there's some sort of parasitic drain and it just takes its battery down to 0 charge and probably 0 volts. So every time you use it, it is completely flat. But let's see if we can get it to work on the power bank. It's not been charging for very long, but let's see if it'll show the difference in temperature between the two sets of heat sinks. Okay, so this is with the unit switched off. You can still see that the cold heat sinks are quite cold. Have I warmed them up there at all? No. And the hot heat sink is kind of down in that gap. So let's turn it on, see if we can see the effect. Right, so I've just switched it on. So it should be warming the hot heat sink. Perhaps I'll see it better over here. And cooling the cold heat sink. Well, maybe the cold heat sink was pretty cold anyway. Not really seeing that. What's the colour palette? Black I think is the coldest and white is the hottest, with red, greens and blues as the intermediate colours. I mean, yes, you can see a sort of general heatness or hotness, high temperature around the cold heatsink, and that the cold heatsink is cold, but I'm not sure that shows it terribly well. Let's try it just with the standalone tech. Right, I need several hands for this, but let's give it a try. So on the power supply I've done 1.5 volts, half an amp, so let's turn that on. It's pulling half an amp, but it's holding, oh yeah, about 1.5 volts as well. Okay, so let's take a look at this. So the hot side is 30 degrees, the cold side is 19.5, which doesn't seem very cold. The hot side, yeah, about 30 degrees, and about 20 degrees on the cold side. I can feel the difference in temperature, and of course you can see it there. It's not very marked. It probably would be if I allowed more current to flow into this element, but clearly you can see that heat is being pumped from the cold surface through the semiconductor junctions between the two ceramic layers and onto the hot surface there. So that's how one of these thermoelectric coolers, this is a TEC. You can get TEG, which is a thermoelectric generator, typically used the other way around, where some of these wood burning stove fans use a thermoelectric generator. So there's the hot side goes onto the very hot stove, and the cold side goes onto a heatsink, and there's a fan, and the idea is it blows warm air from the wood burning stove out into the room. It uses a thermoelectric generator to generate a voltage across different temperature sides to run a very small fan. It's essentially a thermoelectric cooler running in reverse. Now, actually thinking about this, I think the reason the cold side isn't getting very cold is because the hot side's getting too hot and I'm not sucking the heat away. So let's put the hot side on a heatsink and try this again and see if the cold side is any noticeably colder. Not a lot, but yes, a little bit. Now that I'm drawing heat from the hot side into this black piece of powder coated metal, yes, the cold side is getting cooler because we're drawing heat away from the hot side, which enables the thermoelectric junction to work more efficiently. So yes, you do definitely need to draw the heat off the hot side in order that the cold side can get cold. So that is the Silent Night purchased from Lidl. Thermoelectric dehumidifier. It works, but it just is a bit slow. It's got a water tank of 2 litres and it does 600 millilitres per day, so it should fill that in about 3 days. Is that 3 and a bit days? Now that's 24 hours a day. Let's have a look at the tank again. Now, it doesn't look to me like there's more than about 100 millilitres in there, and I've had this running a couple of days, and admittedly not overnight, and probably, I don't know, 8 hours a day. So yes, it's just very slow. It collects water really quite slowly, and the problem with the weather at the moment is it's so rainy outside that it probably moisture creeps into the house as quickly, or if not more quickly, than this thing can draw it out. So it really isn't achieving much. Now I do have an even smaller one of these, this one here, which is 22.5 watts. You can see that it blows the hot air out of the top there, and it's been collecting water again for a couple of days. But this one runs even slower and is thus even more useless. And this is a bit misleading because it says silent operation. Well, it's not really silent at all. The dehumidification process is, because there's no compressor pump, but there's a fan in here and it's actually quite noisy. So no, definitely not silent operation. But there you are, a dehumidifier using the thermoelectric principle. Fascinating to see what's inside and how it works, but not really very practical because it just doesn't have the power to pull significant amounts of moisture out of the air. So at this time of year, you're fighting a losing battle, really. I would recommend the sort of £120 compressor units, which run at about 250 watts, 3 times the power of this unit. They actually do something. This is more of a curiosity, really, but there it is. Cheerio.